Hello, and welcome to this RFMW and Menlo Microsystems webinar. My name is Katie, and I will be your Global Spec moderator. Now let me introduce today's presenter. With us today is Tom Clinkenbeard. Tom is an application engineer with Menlo Microsystems. Welcome to today's event, Tom, and with that, I'd like to pass things along to you to get us started. So Tom, go right ahead.
Hello everyone, and welcome to my webinar titled Choosing the Right RF Switch for High Power Applications. My name is Tom Clinkenbeard, and I'm an applications engineer at Menlo Microsystems. Today I'll dive into all the specs you'll need to consider when choosing a high power RF switch, far beyond what's on the title page of your average datasheet. Before we start, I'd like to quickly thank our co-sponsor, RFMW, who's a distributor for Menlo Micro's selection of high-power RF switches, as well as those from many other suppliers. On our agenda for today, I will discuss the different switch technologies that are available on the market for RF high power. I'll discuss what makes those RF switches high power and under what conditions. And then I'll go through the key specs to look for when you are choosing a high-power switch. At the end of that review, I'll go over two application examples. One will be a switch filter bank, and then the other will be a RF blocking application. As an overview of what different switch technologies are available for high-power RF, there are two main categories of switches. One will be mechanical switches. Those include coaxial, waveguide, and microelectrical mechanical system, or MEMS. And the other category will be semiconductor switches. So those for high power include field effect transistor or FET type switches and pin diode switches, both of which are available in a few different semiconductor technologies, such as silicon and insulator, gallium arsenide, and gallium nitride. A few switches that I won't cover will be CMOS and reed relay, among others, because they are typically not capable of handling high power at RF frequencies. Now, to go over the upper limits of power handling for each of those switch technologies, we can start with waveguide switches. They can reach into the kilowatts of power handling, and they have frequency ranges upwards of 40 gigahertz, but are narrowband switches, so each switch is designed for a narrow frequency band. Coaxial switches can reach the hundreds of watts of power handling and also have frequency ranges that extend into millimeter wave beyond 40 gigahertz. They are typically broadband switches, so they can handle DC power all the way up to whatever their maximum frequency is. Likewise, MEMS switches are broadband switches available up to 20 gigahertz for RF high power. Their power handling can reach the hundreds of watts peak and tens of watts CW, or continuous wave. Pin diode switches are available up to the hundreds of watts power handling and have frequency ranges up to around 6 gigahertz for high power. They are also narrowband, so are designed for specific frequency bands, although typically wider than a waveguide switch. Lastly, FET switches are lower power than most of the other options, extending up to maybe 10 watts, but are also available broadband and into millimeter wave frequencies. Now, those upper limits I mentioned earlier are often only in ideal conditions. As a designer, taking a quick look at a switch datasheet, it might imply that the part's perfect for your application, when in reality, it comes with a lot of trade-offs. Many switches only reach their advertised power handling at a lower frequency than their advertised maximum, or only at room temperature. If you choose the wrong switch early on, it can force a lot of last-minute design changes and delays, and can even impact the reliability if you're using the switch at beyond what it's rated for. Now, knowing how important careful evaluation is, I'll walk through many of the key specs in detail so you know what to look out for early on in the design process. The first spec you'll likely look at is insertion loss. This is usually an important system requirement, but it'll also directly affect the power handling of the switch. A broadband switch advertises 50 watts might not be capable of 50 watt handling over the whole band, and this is because the insertion loss will change and increase at higher frequencies. Talking about the different switch technologies, the semiconductor switches will typically have higher losses than mechanical or MEMS switches. Another consideration will be that semiconductor and waveguide switches are designed for narrow bands. Even if this meets the band requirements for your application, a new design in a new frequency band will require a new switch design. This is why using broadband switches can often save on design time. The last consideration relates actually to the isolation of the switch, another key spec for high power applications. Isolation can be increased by cascading switches, and that will also increase the throw count, but those losses do add up, particularly if you're using a lossy semiconductor switch. The reason why insertion loss is so important for a high power switch, aside from its effect on overall system loss, is that insertion loss directly affects the thermal performance and power handling of the switch. When transmitting high power through a switch, that insertion loss is dissipated as heat. Any switch has a maximum case and a maximum junction temperature, which if exceeded will damage the switch. And so when subjecting a switch to power above its limits, especially at a high ambient temperature, you can quickly go over that maximum case temperature. This is why simulations are important to translate the dissipated power into the specific temperature rise inside the switch, just like for an active component like an amplifier. One important consideration when looking at a datasheet for a high power switch for your application is that difference between maximum case, junction, and ambient temperatures. You might have a 85-degree system requirement and think to choose a switch that's rated to 85 degrees. But if the maximum junction temperature is 85 and your ambient temperature is 85, then the maximum input power is 0 watts, because any more power than that will raise that junction temperature above its limit. The next specification I'll talk about is the size of the switch solution. On the right, you can see a to-scale comparison of different RF high-power switches of the different technologies. Of course, the waveguide and coaxial mechanical switches are much larger than the semiconductor pin diode or MEMS switch solutions. But an important consideration is the total solution size and not just the switch component size. A switch that has high losses and requires heat sink or other thermal management that grows the size of your solution will grow your overall system. Likewise, many switches require external drivers or bias circuits, and that too will add to the total solution size. In later slides, as I compare different switch solutions, I'll be taking this into account, including those drivers and potential thermal management in the total solution size. Size is one specification among SWaP-C, which is an acronym commonly used in the defense industry to define important figures of merit of a system. When comparing multiple systems with similar performance, the size, weight, power, and cost are key talking points. In the case of switches, the weight will typically follow size, and cost will follow the maximum frequency of the switch. But power consumption requires a little bit more care to evaluate. When it comes to power consumption, coaxial and waveguide switches will require the most power to operate, around several watts of power to toggle. Pin diodes require less, around 100 milliwatt per throw, and MEMS require around 5 milliwatts per throw to operate. One thing to note when discussing power is the potential design challenges brought by drivers, besides just their size and power consumption. Pin diodes require negative voltage drivers to operate, which can be difficult to design. They also require supporting components to properly bias the switches and tune performance for a given frequency range. MEMS switches, on the other hand, require high voltages around 70 volts to operate, though at very low current output. One last thing to note is for parts that have internal drivers, they can affect the noise performance of the switch. So in applications that are sensitive to noise that might come from internal regulators or digital circuits, a good idea is to select parts with external driver options. The next specification I'll discuss is peak power handling. This describes high RF power but with a shorter duty cycle. For some switches, the maximum peak power handling might be at or only slightly higher than the average power handling, and for others it might be much greater. In the case of waveguide switches, they have the highest peak power handling, just like with the CW reaching well into the kilowatts. For MEMS switches, they reach much higher power levels for peak power handling, up to 400 watts at 6 gigahertz. This is because the thermal dissipation, particularly at low duty cycles, is much less of a factor, and so the voltage breakdown between features in the switch become the primary concern. Pin diodes can also reach into the hundreds of watts, up to 500 watts below 4 gigahertz frequency ranges. In general, when looking between switches, typically ones with higher frequency bandwidths will have worse peak power handling. This is because the feature geometry inside the switch is smaller, and so arcing becomes more of a risk when dealing with high voltages. When looking at high power switches, one other thing to consider for the switch as well as other components on the board is the voltage breakdown could happen outside of the package. This is particularly an issue at high altitude applications, and so use of underfill and careful line spacing might be required. Linearity is another important consideration when choosing between different high power RF switches. Linearity includes harmonic distortions, such as the second and third harmonic, and intermodulation, such as IP3 and IP2. IP3 is most relevant for any narrowband application, but for broadband, IP2 might also be a concern. Looking at all of the different switch technologies, mechanical switches and MEMS will typically have the best linearity. Semiconductor switches, particularly when they operate near their maximum output power, will have degraded harmonic performance in IP3. Poor switch linearity can impact the total system performance, even if the switch IP3, for example, is 10 to 20 dB better than the amplifier or the other components in the transmit link. You can see on the graph on the top right a comparison of different switch technology, typical IP3, and as well as the overall effect on the transmit link IMD3, which is a measure of the intermod performance of the whole system. When systems don't have the linearity performance they need, they are required to use expensive or large filters to meet the out-of-band or spectrum purity requirements. The next specification I'd like to discuss is the switching time of the various different switch options. Switching time is important for any switch application, but high power may introduce some new considerations. Semiconductor switches will have the fastest switching time of your options, being in the nanoseconds often, but they can have longer settling time if hot switching high power. In this case, it might be necessary to characterize the switch at the specific test frequency and power level to ensure that that settling time is within the overall switching time limits. After semiconductor switches, MEMS switches will have the next fastest switching time in the 10 to 30 microsecond range. Some MEMS switches can hot switch up to a watt with a derated lifetime, but generally it's not recommended to hot switch a MEMS switch. Mechanical switches will be slower in the millisecond switching time range. They can hot switch typically higher power than a MEMS, but it may still reduce the already low cycle lifetimes. The last specification we'll discuss today is insertion loss variation. Insertion loss variation describes the changes in insertion loss that can happen over temperature or the lifetime of the system. For example, with coaxial switches, the insertion loss will typically increase as over the lifetime of the switch. This is caused by the mechanical wear of the contacts inside of the switch. On the other hand, for semiconductor switches, they'll be far more reliable cycle to cycle, but can have variation over temperature. So at 85 degrees, the insertion loss could increase by up to 0.4 dB. This could mean several extra watts of power dissipated in the switch when at higher temperatures. Variation causes thermal issues, and in test and measurement applications can also degrade calibrations. So a sudden drop in yield might happen on a particularly hot day in the lab, or as the system ages, the yield steadily will go down of the devices under test due to these changes in insertion loss. There are methods to compensate for these variations, though they can require complex feedback loops. Thermal sensors can be used to adjust the gain of an amplifier at certain temperatures, but they must require careful calibration of each system. Likewise, feedback loops from power sensors can be used, though they require simulations to ensure that there are no instability that could cause oscillations in the system. Now that we've discussed the various specifications you'll need to look at when choosing a high-power RF switch, I'd like to finish this webinar with 2 example applications and a comparison of how different switch technologies can be used to address different design requirements. The first example is a high-power RF filter bank for a sub-3 GHz application. In this case, I compare PIN diode, GaN, and MEMS switch solutions. As you can see in the table below, the PIN diode solution has the highest power handling limit at 100 watts, but this is at the expense of a significant size increase. This is because of the heat seeking required to handle the dissipated power from the 4 switches, each with half a dB loss. The GaN switch has lower power handling at just 20 CW and a bit higher losses, 0.7 dB per switch, which adds up to another 0.8 dB over the other PIN diode solution. However, this switch has the fastest switching speed of our solutions at 0.505 microseconds. The solution size is smaller than the PIN diode due to the smaller size and lower power handling of the switch, but is still larger than what the size of the switch itself would imply due to the thermal heat sinking required. Since 20 watts is right at the limit of this GaN switch, a lot of heat needs to be pulled away from the switch in order to keep it below the junction temperature maximum. The MEMS switch, having the lowest insertion loss at 0.15 dB per switch and only requiring the 2 switches, means that the solution size is the smallest of all of the options. It's dissipating the lowest amount of power at 1.4 watts, given a 20 watt input power. It has the highest linearity of our options. The second application example we will discuss today is a RF blocking switch for a 6 GHz application. Unlike the filter bank, this application has high peak power requirements and must isolate sensitive receiver electronics from incident high power radar. At this frequency, there are not any semiconductor switches on the market capable of blocking significant peak power in the hundreds of watts. Instead, we will compare a waveguide and MEMS switch solution. Looking at the table, the waveguide switch will have the highest power handling in the hundreds of kilowatts for peak and 12 kilowatt CW. It also has better insertion loss and isolation, but all of this is at the expense of a significantly larger size compared to the MEMS solution. The power consumption, size, and switching speed are several orders of magnitude worse than the MEMS. So in situations where the very high power handling is not required, MEMS will save significant solution size. With that, I would like to quickly discuss Menlo Micro's portfolio of high-power RF switches, and then we will move on to the QA. Menlo Micro has a catalog of 3 switches currently in production available for 25-watt CW power handling applications. And coming in 2025, we will have a RF blocking switch for the 400-watt pulsed application.
All right, Tom, thank you so much for that great presentation. We are going to move into taking some questions from our attendees at this time. All right, Tom, so looking at our Q&A here. First question, are these high power RF switches released to production or just available for engineering samples?
Thank you, Katie. So of the MEMS switches we talked about today, Menlo Micro has 7 products released to production, and we have 3 more to be released before the end of the year, including the RF blocking switch we talked about earlier. We've shipped over 700,000 pieces into the market since our line was qualified in 2021.
All right, thank you so much for that answer. So for our audience members, if you don't get your question answered today, do not worry. We will reach out to you following today's webinar. So feel free to ask as many questions as you'd like, and we will get you an answer. All right, Tom, next one here in our queue. This one is asking, are MEMS switches vulnerable to hot switching?
So yes, it's true that hot switching reduces the lifetime of MEMS switches. So for all of Menlo Micro's high-power RF switches, we guarantee 3 billion minimum switching cycles, cold cycling, with typicals around 50 to 75 billion. However, with hot switching, that'll be derated. We do have derating curves that show typical performance at different power levels, and you should look for that for any MEMS switch. For example, with our switches, hot switching 20 dBm every cycle will show a typical lifetime around 500 million.
All right, thank you so much for that answer. So we have a couple of questions in here, Tom, that are similar. So I'm going to put these two kind of together into one. This person is asking, does a switch replace or work in conjunction with SAW, or which is SAW, or BAW filter? And then this person is asking, are the MEMS switches that you're talking about, are they for cold switching? If they are so, what causes the voltage arcing? So kind of putting those two together for you, Tom, and let me know if you need me to read them again.
Okay, so I'll answer that second question first, actually, with the cold switching. So the voltage arcing you might be talking about will either happen if you are hot switching, so in applications where you might need some level of hot switching, that causes some arcing. We also, during our webinar, talked about peak power handling. And so in that case, even with the switch closed and no hot switching, voltage can arc to other features inside of the switch, whether that's MEMS or mechanical. And so that will define the upper that is if you exceed the upper limit for peak power handling of the switch. And then going back to your first question, does a switch replace or work in conjunction with a SAW, or SAW, or BAW filter? So a switch can work in conjunction with the filter to choose different filters inside the system through software or any other kind of control. And so a switch will allow, at one point, using a filter that filters one frequency and then selecting another. Thank you, Katie.
Thank you so much, Tom, for that answer. So we have a lot of questions in our queue. So thank you, everybody, for your participation today. Tom, next one. Is there a safety issue with having 70V drivers and traces on the board?
So for a MEMS switch that requires a high voltage driver, the current requirements are very low to drive the MEMS switch. So drivers can be selected with a very low output current, and that will minimize the maximum output power to less than 2 milliwatt. And in that case, there's no danger to touching or a safety concern. Thank you.
All right, gentlemen, moving over to our next question. This person is asking, do you plan to offer MM5600 without the need of height gate voltage?
So I assume they mean without the need for high voltage. And so while 5600 is not a high power switch, we do have a product available that has an internal high voltage driver. That is the MM5620. So yes, we do have that, and that is available in production.
Okay. All right. Moving on here. So it looks like there's two that are similar again, Tom. So I'm going to kind of combine these two together if that works for you. So I'm looking at this one first. I'll just read it out. And again, I'll combine it with this next one. What are the effects of VSWR on these switches? And that kind of goes along with, what does cascaded mean? Do you use two or more switches in a series?
So the effects of VSWR on the switch, and this would be the VSWR on the load after the switch, will typically be that into particularly poor VSWR, any power handling limits of a switch will have to account for the reflected power. So with poor VSWR, the forward power and reverse power can potentially combine, and both of those powers together need to be below the maximum power handling of the switch, both for peak and CW. And then the second part of your question, what does cascaded mean? Do you use two or more switches in series? That is the case. And in this case, when cascading switches, the VSWR of the switch itself will need to be accounted for, and so you can, when evaluating the power handling. Thank you.
All right, Tom, next one here in the queue. This person is asking, for the MEMS switches, are there any internal ESD protection?
So for some MEMS switches, there are ESD handling built in. For Menlo Micro, we do not have, we do have some products with the ESD protection built in, but for our high power products, we do not. The ESD protection will typically affect the maximum power handling and the insertion loss and return loss of the switch, particularly at high frequencies. All MEMS switches are typically class 0 devices without ESD protection.
All right. Thank you so much, Tom, for that answer. Okay, so next one here. Again, we have a couple that are somewhat similar, Tom, so I'm going to put these together like I did for the last one. This person is asking, can you comment on the markets where these switches are being used? And then also kind of going along with that is, what are the typical applications are the switches good for?
Thank you. So these switches are used in test equipment and as well as semiconductor test solutions. So these solutions are for testing PAs, high-speed computing chips. In addition, we have customers taking advantage of the high power performance of MEMS switches for wireless infrastructure applications, such as O-RAN and LEO satellite systems, as well as a whole host of aerospace and defense applications.
All right, thank you so much for that answer, Tom. Can Menlo MEMS switches be paralleled for high power handling?
So Menlo MEMS switches at lower frequency applications, typically below a gigahertz, they can be paralleled for higher power handling, as well as for DC applications. So MEMS switches have true DC functionality, and in that case, they can be paralleled for higher current handling as well.
All right, thank you so much for that answer. We've got time for one or two more questions here today. So Tom, I'm just going to go with this one. Are the switches matched to 50 ohms? So
yes, Menlo micro switches are matched to 50 ohms. We do also, for applications that are systems slightly below 50 ohms, for example, 85 ohm differential, we have information available for the performance at that impedance.
Great, Tom. Thank you so much for that answer. So we are going to start to wrap our webinar up at this time. And Tom, I want to say a huge thank you to you for such a great presentation and for taking a handful of our attendees' questions today. So Tom, thank you so much for being here.
Yeah, thank you very much. Thank you very much for hosting us.
Again, thank you all for taking time to attend today's webinar event. Take care, and we will speak with all of you soon.